Great. So next up, we have Qiancheng Fu, who's going to tell us about a system called PReST with refinement session types that are probabilistic. Take it away, Qiancheng.
For instance, the classical deadlock problem of dining philosophers, there's a very simple randomized solution due to Rabin. And for race conditions, there's all sorts of for instance, algorithms based on leader election. And for lossy networks, there's all due to Rabin. Oh, there's no is there no audio? And for race conditions, there's all sorts of for instance, algorithms based on leader election. And for lossy networks,
I can hear you just fine, Qiancheng. Can you hear us?
Oh, there's no.
Hello?
Is there no audio? Okay. So sorry. Lossy networks for retransmission, but these randomized distributed algorithms are hard to get right. It's hard to trigger and reproduce bugs. We can have lots of different kinds of silent errors where programs never crash, but they might produce wrong distribution of outputs. And this could lead to privacy and security risks. It's hard to. So that was the motivation that led to us developing the PReST language. So PReST, which stands for Probabilistic Refinement Session Types, allows for the embedding of probabilistic protocols into types. It features a message passing based concurrency, and it has a probabilistic semantics, and it formally guarantees that runtime behavior matches protocol. So the PReST language extends the probabilistic session types of Das et al., which was first presented at POPL 2023. So in probabilistic session types, we can write a session type like bool here. And what it is saying is that it's going to, on a channel, basically, this channel will send the message true with probability 0.6, and it will send the message false with probability 0.4. So this really defines an interface between a probabilistic client, between a probabilistic server and a client which relies on a probabilistic message. This restriction of probabilistic session types to concrete probabilities limits its expressiveness, as many real-life protocols are often parameterized by probabilities, and these probabilities may also evolve during execution. PReST generalizes the concrete probabilities to symbolic probabilities. So here we have a p-bool type in PReST, which takes in a refinement variable p which has to satisfy the constraint that it is greater than 0 and less than 1. And because if it satisfies this constraint, then we allow it to be used as a probability for annotating the true and false messages. So this is saying that we are going to send a message true with probability p and send the message false with probability 1 minus p. So these symbolic probabilities can both be universally and existentially quantified in the logic. This generalization significantly improves the expressiveness of PReST over probabilistic session types. To realize one of these probabilistic refinement session types in a process, PReST features a flip primitive for generating randomness. So here we have the flip construct, and it takes in an argument p, which is just a refinement expression selected from the interval 0 to 1. And this flip construct says that it will land on heads with probability p. And if it does so, it will execute the code that is written in the heads branch. And it will land on tails with probability 1 minus p, and then execute the code inside of the tails branch. To type check a PReST process, the flip construct interacts with these probability refinements that we have in the types. So for instance here, we have defined a function called makePbool. And what it's going to do is it's going to try to implement a channel which communicates according to the pbool session type. So the idea here is that it's going to execute a flip, and in the heads branch it's going to send true, and in the tails branch it's going to send false. So if we look at the true branch, or the heads branch, we're sending on this channel the true constant. So if we look at this branch in isolation, the distribution of messages sent over this channel is actually just true with probability 1 and false with probability 0, because there's no possibility of false being communicated in this branch in isolation. Now, conversely, in the tails branch, we would have false be at probability 1 and true be at probability 0. Now that we know the distribution of messages in these two branches, we can compute the distribution of messages for the overall flip expression. And this is done by performing a weighted sum over these two distributions. And that gives us the overall distribution of the entire flip expression, which is true at p, false at 1 minus p. And then the PReST type checker will then go in and check that our computed distribution is equal to the one that is specified by the session type. And these kinds of constraints would be gathered by the type checker and then exported to an SMT backend for verification. And then the PReST type checker will then go in. So now that we've seen the basics of using PReST, I want to talk about modeling probability distributions in PReST. So many randomized distributed protocols require sampling from probability distributions. For example, we have leader election. We need to sample from a number of candidates. In crowd forwarding, we need to randomly sample from a crowd of nodes. In the zeroconf protocol, we need to sample from an IP address space. So now the question is, how can we accurately state these kinds of protocols in PReST? In crowd forwarding, we need to if we try to encode distributions like the uniform distribution from 0 to k, we face a conundrum because of this k here. K is just an arbitrary natural number, and this uniform distribution is essentially of arbitrary size. But our flip construct, it only has two branches, so it can only really give us two kinds of results. And our probabilistic types that we've seen before only have a fixed number of possible branches that you could take with some kind of probability. So this kind of creates an issue for us. But we have the key idea that we have to get around this is to actually let probabilities and the refinements interact. So here we define something we call the UNet type. And intuitively, the UNet type is trying to model a natural number that is uniformly sampled from the distribution 0 to n. And notice that in the UNet type, for the suck message and the 0 message, both of these are sent with a probability that is determined by the refinement variable n here. So UNet sends a suck message with probability n over n plus 1, and it sends a 0 message with probability 1 over n plus 1. So if we look at an example, and we try to unpack UNet at a concrete value 3, we will find that a channel of this UNet 3 type will send the message 0 with probability 1 over 4. Because if we substitute 3 for n, we get 1 over 3 plus 1, giving us 1 over 4. For the message trace suck 0, we would actually have 3 over 4 times 1 over 3, because the first suck message comes out with probability 4 over 3, 3 over 4, and the 0 message comes out with probability 1 over 3. So the probability that these two events occur together is actually just 1 over 4. And similarly, if we have suck 0, the computed probability that this comes out is 1 over 4, and then 3 successors is also 1 over 4. So we can actually just conclude that UNet 3 encodes a uniform distribution over 0, 1, 2, and 3. And similarly, if we have suck 0, now our claim now is that the UNet n type encodes the uniform distribution 0, 1 to n. So this is very good news, because at least we have something, and we can verify this claim by hand using just induction. But the even better news is that we can actually automatically verify this using PReST itself. So this is a very surprising discovery. Basically, we discovered that these refinements allow us to encode probing processes to measure probabilistic properties. So here we have defined a function or a process called UNet PMF, which takes in two arguments, x of type UNet n. So this is just basically a uniformly sampled natural number from 0 to n, and a natural number y, which is just an arbitrary fixed natural number between 0 and n. And all that UNet PMF is doing, which I've elided here, is that basically given x and y, UNet PMF returns true if and only if x is equal to y. So all this UNet PMF is doing inside of it is it's just doing an equality comparison between x and y. But we know from basic probability theory that this is exactly the definition of a probability mass function, and that the UNet PMF, it returns true with the exactly correct probability you would expect from a uniform distribution. So the very fact that UNet PMF is well-typed tells us that the UNet type correctly encodes the uniform distribution, and we do not even need to run the UNet PMF function at runtime. So this entire verification procedure is completely static. So now that we have the UNAT type, we can build on top of it much more interesting real-life protocols. So here we have a node in the crowd anonymization protocol. So for this node here, it has a refinement variable I, which is the identifier of the node, and a variable k, which represents the total number of nodes in the protocol. And at the start of the protocol, the node will receive a packet, which has a forwarding target of itself and a final destination of j. If the current node is the final destination of this packet, then we can accept it and then end the protocol. If the current node is not the final destination, then the node will repackage the packet, basically by discarding the target and resampling a fresh, uniformly chosen node as its new target, and then forward that out. So for the meta theory of PReST, we show that PReST possesses the following properties. It has type safety, evaluation of PReST programs preserves types, it has global progress, PReST programs are guaranteed to be deadlock-free. We have probability consistency, that the distribution of communicated messages at runtime always match the specification of these probabilistic session types. And we also have an expected cost bounds theorem that tells us that the expected runtime cost of a program is upper bounded by its cost specification. So in this talk, I did not introduce this cost analysis mechanism. So if you're interested in that, we go into more detail in our paper. So for implementation and evaluation, we implemented a PReST type checker in OCaml following a bidirectional type checking strategy. So this diagram depicts the general architecture of the type checker. So we have an infer procedure and a check procedure. And these two procedures produce large amounts of logical and probability constraints, which are gathered up and then shipped to an SMT backend for automatic verification. So we evaluate PReST on a wide array of benchmarks, and we have a backend using Z3 and a backend using CVC5. So despite these very nasty nonlinear real arithmetic constraints, Z3 tends to perform very well. All benchmarks are solved within 0.3 seconds. CVC5, on the other hand, is not as robust at solving these PReST constraints. They often time out because, from what I understand, is that CVC5 lacks some of these heuristics for Z3 to optimize these kinds of constraints. So for future work and conclusion, in the future, we would like to reason about cryptographic protocols and differential privacy. In fact, that is a project that we are currently doing right now. We want to improve constraint expressiveness and automatic solving with relaxed notions of satisfiability. We also want to integrate ideas from probabilistic program logics to enhance the expressiveness of the refinement logic that we're working with. So in conclusion, we develop PReST for specifying and constructing randomized distributed systems. The integration of probabilistic and refinement types allows for rich specifications and symbolic reasoning about protocols. PReST programs are formally guaranteed to behave according to their protocols. And a type checker for PReST is developed and evaluated on a variety of benchmarks. The PReST type checker performs well on many randomized protocols. So that's the end of my talk. So thanks to everyone.
Thank you, Qiancheng. Let's take a question for the speaker.
The PReST type checker performs well on many randomized.
Well, I have a question, Qiancheng, which is you showed this example where you used a probe program where its type told you something interesting about another program. That was a cool pattern. And I'm wondering, besides sort of probability mass functions that you can look at by sort of giving a type to an equality check, are there other sorts of probes that you found useful in your examples? Probe program where its type told you something interesting about another program. That was a cool pattern. And I'm wondering, besides sort of probability mass functions that you can look at by sort of giving a type to an equality check, are there other sorts of probes that you found useful in your examples?
Oh yeah, absolutely. So it depends on the kind of distribution that you want to verify. So the PMF was the easiest one for this particular example, but for verifying a distribution where we had the sum, or was it the max of two uniform distributions?
Oh yeah.
So for that one,
it depends on the.
we used a cumulative distribution function for that example, and there was another example I don't remember. I think it was the sum or something that we actually had two functions that verify. One was verifying like the front of the distribution, and the second one was verifying like the second partition of the distribution. So you can really. It's very free as to what you do. It's just you just need to make sure that the implementation of these kinds of processes is sufficiently easy to see that it corresponds to like a cumulative distribution or a probability mass function.
It's just you just need to make sure that the implementation of these